Hey guys, it's Josip. Welcome to puzzle number 6. In my opinion, puzzle number 6 is kind of the hardest from this first six puzzles. Obviously, these puzzles are getting harder, and harder, which kind of makes sense. But let's jump into it. As far as you can see, there aren't many opcodes in this puzzle, and we are asking for value. I already inputted some dummy value, which will just set up initial try. So the first opcode is push 1, and this just pushes 0 on top of the stack. If you remember from the previous video, so you have push 1 until push 32. So this opcode will push a different size of bytes onto the stack. And then we have this call data load, and as soon as the call data load is being executed, we see a bunch of values pushed onto the stack. And here, since we 0x11 here, so this is in a way pushed onto the stack. But let's see the exact description of this call data load. So call data load gets the input data of current environment. So it takes one stack input, and that stack input specifies byte offset in the call data. So if you remember, jump takes the byte offset in the deployed code. We have the same concept for the call data. So byte offset is literally saying, let's say my call data is 64 bytes long, but just give me the last 32 bytes, or just give me the first 32 bytes. So byte offset will usually specify, so give me all the bytes from this position. And the stack output is the 32 byte value starting from the given offset of the call data. So that's kind of the thing I've just described. But what's interesting here is that all bytes after the end of the call data are set to 0. So let's go back to our example. So here we just inputted 0x11. And since call data load will take 30, so it will output onto the stack 32 bytes. So in this case, it has to append a bunch of zeros. So this is the first byte, and it will append 31 bytes after that, which are kind of just zeros. But the same thing. So let's take this example. So if this is our call data, if this byte offset specified is 0, it will just output this, since we start from 0 and we give the first 32 bytes. But what's interesting here is we can have a different input. We can have input 31, which would literally say just start from this position, give me whatever that is. But then the outputted value will append a bunch of zeros. So the output, the moral of the story is that output is always 32 bytes, and if this is the end of call data, it will append a bunch of zeros. And this will kind of be crucial for solving this puzzle. Let's just finish the execution. So we have stack is this enormous number, so 1 1, and then a bunch of zeros after that. This is in hexadecimal, so this is an extremely big number, and we cannot jump to that destination, so this will just kind of revert. The key to solving this puzzle is first going in reverse order and first checking. So we're supposed to jump to 0A. So actually this is 10 in decimal. And your probably first guess is going to be I just input 0A. That's it. If we are supposed to jump to 0A, when we kind of So we are like starting the call data load from the byte offset 0. And when this loads, we're just going to like this will be accurate. But let's try it. I'm kind of I'll spoil it for you. It's not this solution. So we have like 0. But what happens here, if you remember, that we append a bunch of zeros. So to this value, we're going to like append as a stack output, a bunch of zeros are going to be appended. So we have this number, and this is like an extremely big number, just like to showcase how big this is. Okay, you can see. So obviously our byte code is the size of our byte code is smaller than this. So this is also not going to work. So since this starts from position 0, actually our value should be like 31 bytes, which are 0, and then the last byte is this 0A. This is actually the same how when you write like uint 256A equals to 5. This is actually like represented with like 31 like 31 zeros, it's actually not 31 zeros, is in hexadecimals it's like 64 zeros, and then like the last byte is just 5. So as I said, like 62 zeros followed by 0A, and here I have the final solution, but let's kind of try it out. So if we run this, we get a 0. Here we get an A. This the EVM codes just kind of omitted all of these zeros from the stack, but here actually on the stack would be like a bunch of zeros followed by A, and this is accurate. Okay, thanks for checking out, and see you in the next puzzle.